This is the Proton Guru video practice for topic 2.3-5. These problems will give you practice on substitution reactions of alkyl halides. Some brief and straightforward reading to get you ready for these problems can be found in the Organic Chemistry 1 Primer 2018 in lessons 2.3-5. You can also find additional chemistry videos and information how to match those videos up with your particular course's textbook at protonguru.com.
Our first problem is a set of reactions, and we are asked to, first of all, predict whether the SN1 or SN2 reaction mechanism will predominate, and then to predict which products we'll get from each reaction. It might be helpful first to list a couple things we know about the SN1 and SN2 reactions to guide us in deciding which one will predominate. For the SN1 reaction, some of the key points might be that it does not work on a primary substrate without resonance because that carbocation is too unstable. It does not require a good nucleophile to work. And if the reaction happens at a stereocenter, this will be expected to produce a stereorandom product, or racemic mixture. The SN2, on the other hand, does not work on tertiary substrates. A good nucleophile is needed, and if you have attack on a chiral center, you would expect the configuration to be inverted in what is called the Walden inversion. We might then go back and label each of our substrates as being secondary, as in the first two cases, tertiary as in the third case, or primary as in this last case. In the case of the tertiary substrate, we know that we can only do an SN1 reaction because the SN2 doesn't work in that case, and we identify our nucleophile that will replace the bromide in that case, so we should get this alcohol as our product. And the reaction center is not a stereogenic carbon. We don't need to worry about which isomers are produced in such a case. In the last case, where we have a primary substrate, we can only do the SN2 reaction. We have an ionic compound here that will produce hydroxide as our nucleophile in solution, just as we had in the third case. So we'll have the production of this primary alcohol by the SN2 route. If we look back at the first two cases, they're both secondary, and secondary work for both SN1 and SN2. The difference between these two reactions is that we have an ionic compound as a reactant here, so we'll be able to produce good nucleophiles. When good nucleophiles are present, we tend to favor the SN2 reaction when the substrate is amenable to it. You don't have to produce a very unfavorable high-energy intermediate like a carbocation as you would in an SN1 case. The last thing we need to note about this first reaction is that the reaction does in fact take place at a stereocenter. We started off with the R configuration of the starting material. We would expect to have the S configuration of the product. In the second reaction, we don't have a good nucleophile. We'll only be able to do the SN1 reaction. And if you have an SN1 reaction with a poor nucleophile, you should produce this product. Now, the SN1 reaction is stereorandom, so you should get a racemic mixture of both of these two isomers. Our next question asks us to, first of all, provide the rate law for the SN1 reaction and the rate law for the SN2 reaction. As delineated in the primer, we see that the rate of the SN1 reaction relies only upon the concentration of the substrate, R with a leading group on it, whereas the rate law for the SN2 reaction, 2 indicating it's bimolecular, the rate depends on the concentrations of two species, the substrate and the nucleophile. With these rate laws in mind, we have two additional questions on this slide. First, we are asked how the rate will be influenced for an SN1 reaction if the nucleophile concentration is doubled. Now, the nucleophile concentration does not show up in the rate law, so it's not going to affect the rate of an SN1 reaction. The last question on this page is how will the rate of the SN2 reaction be influenced if the nucleophile concentration is doubled and the substrate concentration is doubled as well. We start out with this rate law provided here, and if the current concentrations each become doubled, 2 times 2 would be a factor of 4, by which the rate would change 4 times what it would have been otherwise.